So I want to start off with some examples that we'll be using so to get you a little familiar with it before I run into definitions of things you've probably seen before. But I like to use non-standard examples. There's some that are in the textbook that are so standard that it's hard to really see the structure that they're trying to lay on top of what they're trying to show you because you're so familiar with that particular example. For example, if I use the real numbers, well, everybody knows the real numbers. You've been working with them since you've been tiny, and now, just to see it and someone putting structure on it, you're like, well, why can't I do this, or why can't I do that? I've always done this or that. So I'd like to start off with some examples that may not be standard. The complex numbers is a nice example because some of you said that you had complex analysis. Is there a way to shut off that front light? That's back light. Make it any better? Yeah. All right. But complex numbers are interesting because of they're actually not something people are used to working with. Complex numbers are the set of numbers of this form, a plus bi, where a and b are both real numbers. And as you know from many of you teach high school, so you know that in high school algebra, commutative high school algebra, you use square root of -1 is equal to I, and the students think, well, why are they showing me this? It's all imaginary. And not, so they get confused. But of course, square root of -1 can be represented as a plus bi, 0 plus 1i. And in this case, the a and the b are 0 and 1. Just to remind you, if you haven't had complex analysis recently, how to multiply complex numbers. It's Mr. Smiley. You take a plus bi, a1 plus b1i, and a2 plus b2i, and you do the first two, outer two, inner two, and last two. My other I didn't fit there. So then you use the fact that I squared is -1 and substitute that in. And I've just copied the previous section up at the top. You regroup and you get a new number here that is also of the form a plus bi. So that's the reason I regrouped everything, to demonstrate to you that when I take two complex numbers and multiply them together using Mr. Smiley, I get an a plus bi back. That's really important. There's my a and my b.
Will you post all this in Canvas?
These are all going to be video. This whole thing will be videoed, so you'll get to watch it.
What if I don't want to watch it and I'd rather just scroll through PowerPoint?
I sometimes forget to put this up, and if you have a Mac, you can't see it on a Mac directly. There's a way to get to this using, what did Jimmy use? Use Google something to transform it. Yeah, use something. So if you're using a Mac, you won't be able to see the writing on here. Okay, so I'll just remind me if I forget to post it. So just to remind you also that complex numbers, the magnitude, we have a definition of length, or what we mean by the size of a number in the complex plane. And that's the a squared plus b squared under the square root. Now if I have a complex number and it has magnitude 1, for example, then I know that a squared plus b squared is equal to 1. So I can represent those numbers as a diagram on a unit circle. So the imaginary part would be the y value, and the real part would be the x value, and that's really the formula for a unit circle centered at the origin. And what's really cool is that you can express the values that are on this unit circle by something called Euler's formula, which is probably the first thing you see in complex analysis, as e to the I theta, which is cosine theta plus I sine theta. So you really know what those real and imaginary parts are for all of those complex numbers that appear on the unit circle. So that, like I said, this thing is called Euler's formula. So in Fraley's book, he actually recommends that you prove Euler's formula using a Taylor series. So what he means by that, I asked my Georgia Tech students once to prove this, and some kids spent hours and hours trying to solve for I. I thought, oh no, that's not what I meant. I didn't want you to solve for I. So what he means is he wants you to expand cosine theta in terms of its Taylor or its Maclaurin series, expand sine theta in terms of its Maclaurin series, add the two series together, and show that you get the series for e to the I theta, the same series for e to the I theta. That's what they intend you to do. So all of what I just said would be true also for circles of different magnitudes. So if the magnitude of a complex number was not 1, then you could express, you would just have a magnitude z out here. Your radius would be out further, and the point would be considered to be on a circle of a different radius. So why is writing it this way useful? Why did they go through doing this? Well, one of the ways to learn this quickly is to take a complex analysis class, refuse to use that notation, and try to use a plus bi to do everything. So you'll learn very quickly that you're going to be suffering. You're going to be suffering if you try to do that. That's one way to understand why it's useful. I don't think we have time to do that. But on page 14, they have an example where they ask you to find all solutions of z squared equals I. And this is the kind of thing where if you go and put a plus bi squared in there for z and you try to actually solve for the a and the b, it's going to be a massive headache. But if you represent z in the form that I have up here, then z squared is this object right here squared. And then that expands out to the 2 just pops inside here. And I know what this is. This piece is right, the square root just comes off. And then this part here I can expand as a cosine and sine. So all I've done is use the Euler's formula to expand out z squared. How does that help me? Well, I will set that equal to I. This time I'm actually supposed to solve for something. Now the magnitude of I is 1. So that tells me that a squared plus b squared is equal to 1. Right? There's no other way that magnitudes won't match up otherwise. And I also know that whatever's left over, if the magnitude of z is equal to 1, whatever's left over must equal I. Well, that means it doesn't have, the cosine 2 theta must be 0. It can't have a real part. It only has an imaginary part. So I'm looking for solutions where cosine 2 theta is 0 and sine 2 theta is equal to 1. Otherwise, the left side won't match up the right side. So when I do that, so that's why, because I has to be 0 plus 1i. So that's why I get the matchup. That only happens at 2 places on the unit circle. That happens when theta is pi over 4 and theta is 5 pi over 4. So I have 2 solutions. Here's my 2 solutions. Well, you can't see the second one. Now, the second one just appeared. So that's why it's useful. That's one example where it's useful to use Euler's formula to work with numbers on the complex plane. You can reduce those 2 things. Any questions so far? In a graduate course, in my experience from the last graduate course in abstract algebra, there were a variety of different backgrounds. So don't be afraid to shoot up your hand and say, I don't know what you're doing, I don't understand, I have not taken this. It's okay. Because what happens is in our grad abstract class, we get people who have had graduate abstract already somewhere else with an undergrad professor that went nuts, or they've had a abstract algebra class from undergrad that they just despised and are trying to block out of their mind. Or we have some students actually come without a math background and they're getting their master's in math. So we have usually a wide range of backgrounds, but not wide range of abilities. So everybody catches up together. So at the end of the semester, everybody's going to be on the same page. No questions? Too nervous yet? You can always text me or email me if you have a question.